Inductor is a very important device in electric circuit, especially the AC electric circuit. In order to understand the operation of an inductor, we need to first understand magnetism. Here we have a bar magnet. In magnetism, we have north pole and south pole. And from the north pole, there's a magnetic field start, and we can map the magnetic field with small complexes. Now we can bring in the complex here, and the direction of this complex telling you the direction of magnetic field. Now this is north, this is south. Remember, a complex itself is a small bar magnet. So it means this small bar magnet align itself according to the magnetic field. So if I move around, you can see now this is the direction of the magnetic field. And it starts from here, turn here, and then here it reverses its direction. And it start turning, and now you can see the magnetic field points to the south pole. So you can imagine the magnetic field start from the north and then turn itself to the south. But there's a very important point, which is you can see inside when the magnetic field come to the south pole, it's not stop here. The magnetic field continue from the south to the north inside the bar magnet. So an important point here is magnetic field, if you imagine this like a line, is always like a loop. It doesn't have starting point, it doesn't have ending point. It always start here, return back, and go through inside the bar magnet and continues and coming back out here. Now next is, if we move the bar magnet, the magnetic field of course will move. Next, we want to compare the magnetic field produced by the bar magnet, I mean this pattern, with an electromagnet. So you can see here there's a DC source, and in this DC source there is a current flow. So it starts from here, it flows around here. So this current flow here back to the negative side will create magnetic field inside and outside this coil. So let's see how it goes. So this is how electron flow from the negative to the positive. But we know there is the convention current from the positive to the negative. So when the current flow here, you can see it creates a magnetic field. And this magnetic field, it has a pattern very similar to the magnetic field created by a bar magnet. So in a way, they are equivalent. So remember, when a coil carry current, this coil will generate magnetic field, and the magnetic field generated by this coil is exactly the same pattern as a bar magnet. An inductor is an electronic device which based on electromagnetic induction. Now let's look at it. I have a bar magnet here. Surrounding the bar magnet, it generates magnetic field. So I can map the magnetic field with a compact. So this is how the magnetic field generates. It changes direction, and then it moves back to the south pole. And if you look a little bit further, you also get the magnetic field, but of course, because it's further away from the north pole, the magnetic field will be weaker. Within the coil, you still get magnetic field, but it is weaker. There's an important concept in physics which is if we can manage multiply the magnetic field with the area inside this coil, we define another quantity called magnetic flux. So magnetic flux is the multiplication of magnetic field and the area formed by the coil. Now there's a magnetic flux within the coil, but nothing happened. However, if I move the bar magnet toward to the coil, you can see what happened. Yes, you can see there's a current flow around the coil, and because of the current flow, it also creates voltage across the two ends of the coil, or we can say it creates EMF. Now, this time here, if I move the bar magnet away from the coil, it also creates current flow and EMF. It means there is energy created. So the question is, if there's a magnetic flux here, you won't generate any EMF or any current. But if I either increase the magnetic flux by moving the bar magnet closer to the coil, or reduce the magnetic flux by moving the bar magnet away from the coil, both cases will generate current flow and also the EMF at the end of the coil. In conclusion, if there's a magnetic field passing through the coil, they create a magnetic flux, but the magnetic flux itself won't create current flow or the voltage. It is the change of magnetic flux. It means either I push the magnet toward or away from the coil, and you can see the flux within the coil will either increases or decreases. It is the change that creates the current flow or the EMF across. Let's look at how inductance is defined. So we have a coil and there's a current passing through the coil. And from the basic electromagnetism, we know it will generate magnetic field. Mathematically, the magnetic field will be represented by B, and it is a vector. So this magnetic field generated by the current will create a magnetic flux. Magnetic flux is defined as the area A multiply the magnetic field. Because there is many turns in a solenoid, so the total magnetic flux must equal to N multiply A times B, or simply N magnetic flux, because A, the area, multiply the magnetic field, we call this one flux. Now, this magnetic flux within the coil must proportional to the current. The higher the current, the stronger the magnetic flux. And this proportional constant is inductance. So this is our inductance. So let's compare with capacitor. In capacitor, we have metal plate, and this metal plate will store charge, positive or negative. How much charge is stored, and it is proportional to the voltage you apply across this one. The voltage here, the proportional constant is C. So can you see this is how we defined the inductance, and this is how we defined the capacitance. So both C and L, they are the proportional constant, but in a different configuration. Therefore, when we rearrange this one, L is defined as number of turns multiply the flux. This is the flux through each turn. I is the current through the coil. This is just similar with C, the capacitance, defined as the charge per unit voltage. Now, Faraday's law of induction is equal to E minus number of turns multiplied the change of magnetic flux. So what it means is, when you have a current here, you have a magnetic flux, but if this time your current starts changing, so when I say change, it can be from 2 to 3, from 3 to 2, or even from 0 to 1 ampere. It means whenever the current change, the magnetic flux here will change. And the Faraday law of induction say, if the magnetic flux change, you will create a EMF. It means you will create a voltage across both sides of this coil. Now, this is what it means here. If we combine this one with our definition, of course, we can change this one to this format. Again, the magnetic flux is proportional to I, and the proportional constant is L. This is the definition of inductance. Combine these two, you will find if the current change along the coil, you will have a EMF. It means this is measured in volts, and this one is measured in Henry. Okay, so the important is the change in current. In electrical circuit, L is represented by this symbol here. And if we connect a L with a R and we imagine you just close the circuit, you will find the current used at the time you close is equal to 0. The reason is when there's a current flow, it tries to flow, it will introduce a magnetic field. And this magnetic field will create a magnetic flux. This change of magnetic flux in the coil will create a EMF. So if this is say 5 volt, 0 volt, the induced EMF will opposite to this one. It means the induced EMF will also 5 volt, 0 volt. It means it's opposite to here. And this is 5, this is 5. So it means at the moment you close the switch, there is no current passing through. But this cannot be lost. So that is what happens. The current later will gradually increases and increases until it reaches as if the coil now become like a conducting wire, and the current now determined by V over R. The time constant is L over R. And the rise of current is described similar as a capacitor, 1 minus E. Now, this time 1 minus E. Remember, in capacitor, V is as a function of T is V naught 1 minus E minus T over RC. And we say RC is the time constant. Now here, this is minus, I beg your pardon, minus here. So T over, now this time, the time constant is L over R. So minus T L over R can be written as minus RT over L. Therefore, you will see RT over L. Remember, there's a negative sign here. Also, like capacitor, if you have a capacitor here, we'll ask how we can make this capacitance. And we say capacitance is proportional to area, inversely proportional to the separation D, and the proportional constant is permittivity of free space. Now the same argument, how would you make a specific L for an inductor? And this is equal to n square, number of turns square. It is proportional to the area of the coil. So this A, the larger the area, it is stronger the magnetic flux or the inductance. And here is L, it means the length of this one. And there's a proportional constant like capacitor. This time the proportional constant mu naught. Incidentally, this value is a constant 4 pi times 10 to the minus 7. And this one 8.854 times 10 to the minus 12. And both these two, they are constant. Let's go back to week 5 workbook. Here it summarizes the key relations. The induced EMF is proportional to the change in current, and the proportional constant is L. This is our inductance, and it is measured in Henry H. This relationship is equivalent to our capacitance in this case. Remember, in a capacitor, Q is equal to CV. So I equal to dQ dt. So this is equal to C dV dt. So this one say the current flowing through the capacitor is equal to the change in voltage, and the proportional constant is the capacitance. Next, how to make a inductor. This is proportional to mu naught. Mu naught, this is called permeability. Permeability of free space. This is our mu naught, and it is equal to 4 pi times 10 to the minus 7. And it also proportional to n square, the number of turns, the area of the coil, and this is the length of the coil. The capacitance counterpart will be the C is proportional to the area, inversely proportional to the separation of the plate, and the proportional constant is epsilon. Epsilon is called permittivity of free space. This is a different from magnetic case, and this is equal to 8.854 times 10 to the minus 12. The energy, yes, a inductor store energy within the magnetic field. So it is equal to the inductance and I square. And the counterpart of capacitor is half CV square. So example number 9, calculate the inductance of a solenoid, which is 1.5 centimeter long, 3.00 millimeter in diameter, 300 turns. The L is proportional to N square A over L, and this is 4 pi times minus 7. This is the permeability of free space. Number of turns, 300 square. Now this is diameter, so the R radius is 1.5 millimeter. It means 1.5 times 10 to the minus 3. So it's a pi R square. The L, 1.5 times 10 to the minus 2. They're all in meter. So the value becomes 5.3 times 10 to the minus 5 Henry. An inductor carry a current of 2.5 ampere. Magnetic energy stored in the inductor is 0.0035 joule. What is the inductance? So remember, the energy stored is half Li square. So L equal to 2U over I square. 2 times 0.0035 joule, and the I is 2.5 square. So the inductance becomes 1.12 milli Henry. Number 11, an inductor with L equal to 1.5 milli Henry connect to a circuit that produces a current increase steadily from 1.5 ampere to 5.6 ampere over 2.3 seconds. What is the voltage across the inductor? So this is an inductor. If the current passing through the inductor increases, so that will induce a EMF. So the EMF it induced, which is V, or sometimes you can use EMF. It doesn't really matter. And this is proportional to the change of current. And the proportional constant is the inductance. So let's look at inductance is 1.5 times 10 to the minus 3. And the change is 5.6 minus 1.5. And it takes 2.3 seconds. So it is equal to 2.67 millivolt. Number 12, a coil of inductance 20 millihenry carried a current increase at this rate. Find the induced voltage. So this is similar. A, the induced voltage is proportional to the inductance, and this is di dt. So this is 20 times 10 to the minus 3, and this one is di dt. So this is 204 volts. B. If current reach 1 ampere, find the energy store. Energy store U is half L I square. So this one is 20 times minus 3, and the I is 1 square, so it's 10 times 10 to the minus 3 joule. C. Compare with a 100 microfarads and the charge and the change to 10 volts store the same energy. What current in this inductor? So first look at how much energy stored in this capacitor. So when the capacitor charged to 10 volt, the energy for the capacitor, the energy is half C V square. So this is half, and this is 100 times 10 to the minus 6, and this is 10 square. So this is equal to 0.005 joule. So it asks what current required to have the same energy store. So for the inductor, so we assume we have the same inductor. It means U equal to half L I square. So the U is equal to 0.005. So we want to find I. So I is equal to 2U over L, take square root. This one is 2 times 0.005, and the inductance is 20 millihenry. So this is 20 milli. So the current equal to 0.707 ampere.